Ben burasını sen kenara edersen şuradan başla.
Tamamdır. Hello everybody. As we talked about last week, we have a guest speaker today, Mustafa Çamurli. He is one of our graduate students. He graduated. He took his both BS degree and MS degree from our department. He worked with Didem Hoca, I guess.
Right.
He has lots of experience about virtualization, and he asked me to share his experience with us, and I said that's very welcome. He works for Siemens. What is Siemens? Is Siemens anonim şirketi in Turkey? Yeah.
Correct.
Siemens Corporation. I don't know. He's going to give us some information about the company that he's working for, and then he'll talk about virtualization, containerization, and cloud. Some virtualization, right? We were already talking about this. So, microphone is yours, Mustafa.
Thank you very much. Hi everybody. Mustafa Çamurli again. So nice to meet you all. First, I just add a couple of things on behalf of myself and Siemens, and we will jump to the topic. So, almost 11 years ago, I graduated from here, and almost 13 years working for different roles. Currently, I'm working in Siemens as Chief Software Architect, almost 7 years. Siemens is a very big company, as you know. So you probably know Siemens from home appliances, right? So you know fridges, ovens, and etc. So, but this is just a small portion of the company. But most importantly, for you to know, Siemens is a very big software company. Probably, we can consider it one of the top 10, I guess, because Siemens is working in a lot of different sectors, software involved, especially in industry. So, in energy, automation, production industry, health and years, electrification, almost every sector, so software involved. And particularly in my division, I'm working in motion control. Again, we are in the digitalization portion of this division. So in Turkey, there are 600 people working in the R&D. So this is an already big number for Turkey as well. So there are communication, cloud, energy. I'm not sure for health years, but we are using every technology what you're seeing nowadays. So embedded, cloud, desktop applications, mobile, and everything. So I highly suggest you to consider at least touching the Siemens with your internships, maybe some of junior job vacancies. So it will be really nice to have you there as well. So because I know the university, I know all the graduates, very qualified from the beginning to the end. So I know all the curriculum here. So I know all the professors. So you are going through very, I think, hard process here in terms of getting yourself being up to the academia as well as industry. So again, Siemens is a very promising company. So just consider it as one of the candidates for yourself. So today I will talk about virtualization, containerization, and cloud. So I will cover a little bit textbook information at the beginning for the virtualization. So I'm not sure if they are responsible for any homeworks or midterms and exams, but I try to make sure you understand what is virtualization is, okay? So, and we will touch containerization, which is biggest breakthrough almost since 2007 or 8. With the containerization, we can talk about cloud, what it is now, right now, nowadays. So I will get you understand what is Docker and maybe a little bit if we get a chance, I will share a little bit hands-on experience with that. And we will talk about a little bit cloud as well, because all the virtualization and containerization things meant for the cloud, because currently cloud is a big hype, and the virtualization and containerization is backing this up very heavily. So, and I'm not a native speaker, and if it is kind of ambiguous or which you don't understand, please stop, and I try to express myself in Turkish as well, okay? So, okay, so this is the agenda. Let me, Hocam, how can I make this shared? I didn't share it, hold on, sorry. All right, yeah, good. So we will talk about conceptual view. So this is the most important part, because you will probably know what is virtualization is, because you maybe touch a couple of tools right now, what you're using, VMware, VirtualBox, and etc. You can have this installed on your desktop. So, but we're going to talk about what is really the virtualization is. And we will look about a little bit of history, how it is developed, and purpose of the virtualization, and a little bit technical stuff about memory and Io virtualization. And I already watched a couple of YouTube records from previous courses in operating systems, so you're touching heavily technical side. So I try to cover that as well a little bit in this memory and Io virtualization, and maybe in the next hour, so we will touch containerization and Docker, and we will compare virtualization and containerization, and we will lastly touch cloud a little bit. Okay, so conceptually, virtualization is saving resources. Okay, so back in days, what we have is physical resources. We are not talking about right now for ourselves. We are talking about the big companies. Okay, what they have, big physical machines, which we call mainframes, and they are running all these applications in these mainframes, and they are physically allocated piece of, big physical hardware, and they are running their software in it. But it's always beginning of 60s and 70s, always a wonder for the scientific area and also industrial area. How can we use these resources efficiently? So if you think about the software, even which you have written in your daily life, so software cannot, maybe is not meant to, but cannot allocate all of those resources what operating system or hardware presents, right? So there are tons of big resources currently we can scale up vertically. So we will touch into this topic also. So what is vertical scaling is, so we can scale up our hardware, right? So we can buy 16 gigs of RAM and can scale up to almost, I can't sure, but it cannot go for the x64 architecture, it cannot go up to beyond 32 gigs, but yeah, you can make it up to this big numbers. In terms of processing power, you can upgrade your processors as well. But if you're running small portion of the software, so it really doesn't matter for this physical resources. So instead of using this resource efficiently, we have to make this shared resources for different softwares, which is already understandable because you can run multiple software copies in one operating system, right? So which we are already doing. So we can run our Outlooks, we can run our IDEs, compilers, and etc. But if you think that if they are running in one system, they are kind of vulnerable to each other. So if one of the software is crashing the OS, so OS completely useless. So we know the blue screen of that, right? So if you're running a critical software next to the Outlook, you cannot trust Outlook, right? It's not only stability, it's also for security. So this idea encourages the virtualization so much. So which is the idea sandboxing comes into place, how we can isolate these processes. Okay, so first idea is in order to isolate these processes, so we can let's introduce a layer, so we can isolate, so we can emulate the hardware, so we can run multiple OSs on top of hardware. Okay, so this is kind of a sandboxing idea where it's come from. So another motivation is, as we talk about different software where we are running, so they are kind of risky to run them side by side. So you can run different softwares and different operation systems, not for just scalability or anything, just for compatibility, because not all software is running in industry working in Linux. Maybe they are running on OS, Mac OS, maybe in Windows. So this is kind of a necessity for the big companies having different operating systems, okay, running in parallel. So as you have a big machine, so you can just scale up. Installing the virtual machines, you can scale up horizontally. So we'll come to that point as well later on. So one of the main thing is hypervisor. If you think about virtualization, so this is the concept actually which is introduced. So we will see the hypervisor types, how it is working, where it is abstracted. So what it is providing to the host guest OSs. So ideally, which we call hypervisor, which enables guest OS running in the same single computer. Okay, so you probably heard about this term as well, hypervisor. So again, the idea is we are gonna isolate and protect these applications, okay, from each other, from the system, and also we're gonna have some failure isolation if one of those applications crashes, doing some malicious things so we can protect others, okay? And virtualization is kind of an emulation. Probably you know the emulation from gaming a little bit. So what emulation is, it is not really running into the physical system. You are emulating the physical system, okay? Just like requiring an processing power from CPU, you're emulating the virtual memory, you're emulating all the disk, you're emulating the other IO things. So virtualization is kind of an emulation, okay? And we are gonna look at the hypervisor thing. So they are doing emulations pretty much, but not 100%. So doing 100% emulation is kind of killing us. So hypervisors doing the emulation as less as possible when it is required, okay? And another concept is not full virtualization, but also para-virtualization. Maybe we can call semi-virtualization. So ideally, virtualization is you can install identical OSs, what you can install on the physical machine. And this is a full virtualization because ideally OS cannot distinguish. So this is a VM or this is a physical computer. But para-virtualization a little bit in the middle. So you're providing an API for the for the guest VM. So they're not using the system just like a physical system, but they are using the system like a software. Okay, they are calling certain APIs to use system resources, to use the scheduling things, to use the memory, to use the disk and all the peripherals. So this is what we call para-virtualization. And one of the biggest things actually previously, before the virtualization is invented, is the migration. So it is really hard to migrate a single process. If you think the process, you already know, process has a bunch of dependencies, a bunch of resources in terms of signals, all the stack variables and a heap, what is allocated dynamically. I don't know so all the files and handles and etc. It is really migrate one process, one system to another, because you need to bundle up all the things and put it in a new system, and it's highly complicated. And you know that also forking a process as well as really, let's say, complicated and costly thing. So if you don't copy the process, but copy the whole system, it is much more easier because you can take the snapshot of the disk, take the snapshot of the memory, and put it in a new system as a guest, and it's run immediately. So it's really easy and encourages all the industry to switch to virtualization technology. So let's just consider you're running a system, big system, very critical task, and you got a hardware failure, and you need to speed things up in order to recovery. So you can just copy one stuff to another physical machine, and all the software is up and running. So if you know many cloud providers doing some sort of SLA, so which means service layer agreements. So most of the services what you are using right now, maybe YouTube, Spotify, all the free or paid resources, guarantees almost 99.9999. So they are calling 6 nines, 8 nines. Availability, this is how they tackle of this problem. Okay, so they are using tons of virtual resources and they're copying stuff all over the place to make it redundant, make it easy to recover. And so this is virtualization is the most suitable technology for the cloud, and we are going to touch the why it is important and in the later slides. Okay, so let's talk about a bit history. So the IBM started research 1960s as a research project. So you can read all the history because there are specific bunch of software and hardware, because IBM is the king of all the software and hardware business in 60s and 70s. So they would like to use their resources as good as possible, as efficient as possible. So they started the virtualization. Okay, and then theory was found in 1970s in the UCLA from two professors. I couldn't remember those names, but this is what we are using right now. Okay, this is a true virtualization. So, but in this time, the architectures are not ready to adopt this, and we need to wait for some sort of physical development in the processors and mainboards and etc. And then 1990s. VMware, so virtual machineware. This is kind of an analogy to the software and hardware. So this is named how this came up. So VMware is invented. This is really the father of the system what we are using right now, and VMware Workstation and Parallels in the macOS, and VirtualBox as well for the alternatives. So this is invented 1990s, and this provides actual virtualization running all over the place. Okay, so purpose in virtualization. I would like to take you a little step back and asking the question, do you know the movie of Truman Show? How many of you know the movie? So can anybody tell us what was it about?
What is the name of the movie?
Truman Show. Jim Carrey started. Can anyone? In Turkish as well, no problem. Yeah.
There is a man, Jim Carrey, and his life is a 27-24 live movie.
Exactly. So and the man doesn't know exactly. So we know, right? We know from the viewer point of view, the whole world in Truman is living in is an artificial world. So it is kind of a made up, but Truman doesn't know what it is. So the purpose of the virtualization exactly that. So Truman doesn't know if it is a real world or artificial world, and it is designed that Truman cannot escape the world. So the virtualization exactly that analogy. Okay, so purpose of the virtualization in two sentences. So programs cannot distinguish from real or VM machine. Okay, so they cannot understand. So if they do, this is not a real virtualization, and programs cannot escape the VM, even if they understand this is a really VM. So if can somehow sneak up to the real VM, that this real OS, so this cannot be possible. So this is the two main purpose of the virtualization. So these are the two main problems should be tackled in the virtualization. Okay, so these three criteria are formally listed. So safety, so VMs running on the host cannot crash the system, cannot crash the physical world in they're living in. So fidelity means they really cannot escape. Okay, they should live in boundaries. And efficiency means so VM environment should work as efficient as like they are running in the real system. Okay, so they are running in the VM, but hypervisor is kind of translating all the instructions they are needing, but not all the instructions are translated. Many of the instructions are directly running in the CPU, but little bit set of instructions, there are privileged instructions. So as you know, context switches, IO demanding things, memory demanding things, page faults, all the things are critical instructions, privileged instructions. So they must do some sort of translation to the real system. Only this portion of instructions should go through hypervisors, with respect to some emulation, some translation, due to some traps. But most of the instructions consider some mathematical things, so other business-related stuff, comparing other things most of the CPUs are doing should run on CPU without any obstacles, okay? And we need to touch here a little bit vertical and horizontal scalability, because we need to understand why virtualization is helping us, how we can most use most out of it. So the scalability is the biggest concern in software. Okay, so if you're implementing a stuff, so you need to consider actually what is the user doing with my software, how many user is going to touch my software, and what is the scaling point of my software. Is the user interaction or the mathematical formulas, maybe graphical things. So, and you need your software responsive all the way up to the all the requirements so demanded from the users. So if just consider the scenario where all the internet shopping sites, so they are not getting traffic 100% all the day of the time. So they are getting traffic, which we are also touch this with the Amazon Web Services story, but they have to be scaling up to very big numbers in order to give their services. Okay, so scalability means software should run as required in given conditions in terms of what they are doing. So vertical scalability, as I touched in the beginning, putting extra physical power on top of what we are. Okay, so if you are running a software and if you think which is not enough in terms of CPU, what you can do is you can put more CPU power, changing CPU or putting another CPU next to it. Or if you demand a memory, what you can do is in terms of vertical scalability, you can put another RAM next to another. So this is what vertical scalability means. But if you think it is not a practical thing, right? So if you're running a software, if you think this is not enough in terms of requirements, so if you're going to upgrade the physical thing in terms of vertically, you need to stop the firmware, stop the software, and you need to shut down all the system, you need to upgrade it and run it again. So this is kind of a hard thing to do, and not many vendors or service providers would like to do it. So instead, they would consider horizontal scalability. What horizontal scalability means, you are running the system, and if it is not enough, you are launching another instance next to it. Okay, so if you think about it a little bit, this is where virtualization comes into place. So if I'm running a second instance of my software, I would like to have it as secure as in the first instance. Okay, in the first instance, there is no software next to it running. Okay, but if I running the second instance, it's kind of maybe they're just running against each other in terms of resources, right? So in order to isolate those things, virtualization is the best tool for you to do. So what you can do is you can install second VM next to in the first one, and then you can launch your second software. Okay, and then you immediately get your resources up and running. Just clip of a second, and you have a very good scalability. Okay, this is what horizontal scalability is, and probably this is, if you think about operating systems, this is the most important thing. So okay, as a concept, so please don't forget it. Probably you might get asked, not in the first interview of yours, maybe second and third. So scalability really important, and horizontal scalability is more important than that. Okay, so do you understand the concept? This is really cool thing, and this is what virtualization is pretty much. This is why I would like to touch it a little bit. Okay, so let's speak about the technical stuff, and let's touch the hypervisors a little bit. So hypervisors, what virtualization is. So they are doing emulation They are doing trap and emulate pretty much. So they are putting an abstraction layer on top of physical system, and they host all the guest VMs. Okay, so we have two types of this is all. So we have two types of hypervisors. Type 1, allocating all the hardware resources. They are like an operating system. Okay, there is no other software running in the hardware on top of hardware. So this is the type 1 hypervisor. Complete software allocate the whole physical resource and provides the virtualization environment up to the operating systems they're running on top of hypervisor. So these hypervisors controlling all the hardware stuff. Okay, they are really like an operating system, but not the real operating system, because as you know right now, operating systems are doing complicated things. Hypervisors only doing some sort of control and translation, okay, and management as well a little bit. So we will talk about in the memory and Io virtualization. And what they are doing is, so they are controlling all the system calls, let's say, okay. Normal instructions are go through the hardware without any intervention. So hypervisor type 1 getting all the system calls, all the privilege instructions, doing some sort of management and translate things, maybe translate pages, translate signals, translate this content, okay, and getting the actual trap, getting the actual signals and interrupts, translate those things as well, and just communicating with the hardware. So providing, just like they are running, providing the OSs, running on top of hypervisors, just like they are running in the real hardware. Okay? So on the other hand, type 2 hypervisors, a little bit lightweighted. So what we are running in our desktop PCs, actually, they are really virtual boxes, VMwares. Okay? So they are running on top of host OS. If I install Linux, so I can install VirtualBox on top, and VirtualBox provides some sort of virtualization, and this is also good for many reasons. Maybe it's not really practical for the industry, because most of the industry is running type 1, because this is what is meant for. So just think about Google. They have tons of physical machines, and they don't need to run their operating system at all. So they just install vSphere, mostly used, and vSphere allocates all the resources for them. And if you just ask a machine, just the operating system from Google Cloud Platform, it spins up a VM for you, Linux VM for you, and it give it to you. This is a complete VM. But on the other hand, type 2, what we are using in our daily work. So if I need to run some sort of software runs in the Linux, so what I can do is I can install type 2 hypervisor on top of my Windows or Linux, and I can just do all the work on behalf of myself. So type 2 hypervisors similar to type 1, but they are not allocating all the hardware. They are just a software, okay? Just the Windows software. So they are running, as you might guess, they are running in user mode, okay? Because as you know, OS running, controlling all the modes, kernel modes. So what they are doing is they are try to communicate with the host OS and translating all the necessary guest OS instructions, just like running it in the hypervisors, okay? So if host OS demanding a page, just a memory with the malloc, and this is let's say in the new allocation, and it requires some sort of page manipulation, hypervisor 2 just handling it as it is doing it by themselves, okay? So host OS doesn't know the guest OS running on top of it. It only knows the hypervisor demanding all the resources for itself, okay?
Mustafa, I have a question.
Yes.
Type 2 hypervisor, if the guest operating system wants to set up a new interrupt table, it thinks that it is running on a hardware.
Yeah.
And type 2 hypervisor is supposed to translate this request through the host operating system.
Right.
Host operating system doesn't have any system calls to set up the interrupt table. Right? I mean, you don't let your ordinary processes to change the interrupt tables or to do anything about the interrupt.
Exactly.
So how does it work?
So Hypervisor 2 uses some sort of special interfaces in the host OS, because host OS supports virtualization as well. So ideally, virtualization kind of supported in the hardware level, and this hardware capabilities should be enabled by the host operating system as well. Okay, so ideally, you don't, if you're an operating system, you don't want anybody touch these hardware resources, right? So you put an isolation layer. Let me, my mouse, cursor, no, it's not there. So ideally, you don't want anybody to go to the hardware, right? So you don't want anybody up to this level, go to the hardware. So you are full in control here. And most of the hardware resources right now really provide a good virtualization in hardware level. Okay, so of course they're not running in the kernel mode, but they are some sort of really good accelerations, which we call VT. Maybe you just know if you're just browsing in the internet. So most of the Intel hardware, the AMD hardware provides VT, virtual technology, in the hardware level. And most of the software and host OSs provides this functionality up to the guest OSs, to the hypervisor. And they are using some sort of special APIs from the host OS, providing this kind of privilege instructions, manipulating this kind of hardware resources through privilege instructions via the APIs. Okay, so this is not a para-virtualization, but it is type of this. Okay, so type 2 hypervisors is providing actually a full virtualization, but if you think about that, it's kind of a para-virtualization because all the necessary things provided by the host OS. They are not using the hardware, but they are using special interfaces from the host OS. They are just kind of allocating these resources from direct to physical interface.
Is that the reason why it takes longer to install VMware on?
Yes, that's right. So because all the privilege instructions should be intervened by the hypervisor, should be translated via the host OS to the hardware. So they are taking, especially if they are running a VM, doing a lot of network transfer, a lot of disk operation, it takes tremendous amount of time compared to the hypervisor one.
I'm talking about installing the VMware.
Installing the VMware.
Yeah.
I'm not sure if it takes up much time.
Well, it is not as simple as installing a program. You need the
hypervisor itself. Okay, got it. Yeah, of course. So they are kind of installing probably some sort of drivers into the host OS. This is why it takes a little bit more time. So I'm not really comparing this stuff. But if you think about running a guest OS on top of hypervisor 2 compared to 1, probably this takes a lot of time because intuitively one stack up. So as your software runs, if you're implementing a software, a lot of stacks on each other. So if the higher level, if it gets the higher level, it slows down because in order to do the things in CPU, you need to trace down a lot of steps. Okay, so ideally this guest OS running slower than Windows and Linux because a lot of API software translations here. So in hypervisor 1, also software translations, but less than this. Okay, this is a lot of traps going on in terms of disk and network. So if you're running, let's say, a simulation based on mathematical calculations in running here, guest OS, it really doesn't matter if you're running it here or here because all the instructions immediately translated here all the way up down to the hardware. Because you are doing LAU stuff, okay, arithmetic logic unit stuff. You're not doing IO interrupts. You're not doing, I don't know, network interrupts. So there is no IO going on. You know, right? IO bound or CPU bound processes. You know that, right? Yeah, you know all the difference between. So IO bound operations, you need to wait for something to happen. So it's kind of an asynchronous things. You need to put something and wait and get it. So CPU on the main while just providing other things to the other parties of the software. So, but if you're running CPU bound operations, what you are doing is compare stuff, adding stuff, calculating stuff, conditionals, right? And it's really fast in the virtualization too because all the instructions not getting trapped because they're not really meant to be get trapped. Okay? So this is pretty much what type 2 and type 1 hypervisors. So these are the difference between. So
which one is more complicated?
Type it depends. Of course, answer of all the questions because type 2 is implementing the stuff what host OS provides. So they're implementing the APIs. they install a couple of drivers. I can say this is the much more easier to implement because you are running on top of software, and it is like implementing a device driver, nothing else. Okay, because OS already providing all the abstraction from the hardware. You don't need to tackle all the problems in the hardware. OS already doing a bunch of stuff for you. So you're using interfaces, via device drivers, and what you are doing is pretty much in type 2, managing page tables, maybe managing all the disk technology transformations. Just like if the hardware is a SCSI or RAID supported kind of disk, on your host OS knows on the IDE interfaces, hypervisor should translate all the technology all the way up down. Okay, so hypervisor knows the SCSI interface disk, and it knows the RAID couple of disks next to each other. Do you know RAID? RAID, couple of redundancy things, make things more sustainable, stable, etc. So this type 2 is only translating this kind of stuff. They really don't care about the hardware. But type 1, sitting in the hardware, they have to deal with all the hardware stuff. I believe this is most of the type 1 code probably includes pretty much assembly code in order to use most efficient features from the CPUs as well. So I think type 1 is the complicated one, as I think right now. So maybe it is up to you to make a little bit search for yourself. So this is what I can come up with. Yes?
When you're executing these special API calls from the type 2
Yeah.
hypervisor trying to communicate with the hardware itself, do you have to go first to host OS and
Exactly,
then to hardware,
that's right.
or directly to hardware?
No. You need to go to host first and the hardware second, because you cannot touch the hardware because host OS manipulating all the stuff. So think about kernel mode or user mode. So hypervisor 2 is just like a process. So
Two context switches.
So we can say one context switch. So if you look on the guest OS point of view, two context switches, right? So but you can consider it as a one whole. So if your process is running in the guest OS, so if you're demanding a page or some sort of IO, you just get switched. You get trapped because hypervisor tells you, okay, wait, I'm gonna get you what you have or what you need, and then just context switch happen in the guest OS, and then hypervisor tells the OS, just get me what I need. Probably what is running on the host OS, again, type 2 hypervisor should wait for it. But guest OS doesn't know where there's a context switch in here as well. So if you think the type 2 hypervisor, there's only one context switch because it is running a program here demanding resources from host OS, only one context switch. But overall, we can say two context switches happening if you look at point of guest OS. Is that what you asked? Okay.
Does type 1 hypervisor provides sort of scheduling algorithm for switching the operating systems?
No. Type 1 only provides the hardware virtualization. Okay, it doesn't care about any operating system capabilities. Okay, it doesn't provide any scheduling. Okay, it only provides a layer to the operating system, and operating system sees the hardware as whole. Okay, so scheduling really concern of an operating system. So if you have a bunch of processes, you need to give a fair scheduling. Hypervisor 1 really doesn't know how many processes running on top of itself. So it can be thousands of processes running in the type 1, on the type 1, but type 1 doesn't know what it is. Okay, type 1 only sees the operating system itself. So let's see, there's a process here, wants to get some CPU cycle. Okay, so hypervisor just give the resources, a portion of the resource. Maybe hypervisor allocates CPU 1 to Windows, CPU 2 to Linux. It does this isolation. Okay,
so we have more than one CPU.
Could be. If you want CPU here, type 1 doing maybe hard kind of, let's say, portioning. You got 5 cycle, you got 10 cycle, and this is all it is. It's because hypervisor cannot know priority, cannot know IO demands and anything. Okay, this is kind of a context of the operating system. This is really special to the operating system capabilities. Okay, this is really, I don't want to say thin layer, but it's not an intelligent layer. That intelligent. Okay, Any questions? Yeah.
If you have one CPU,
Yeah.
how can CPU switch between if hypervisor don't know?
Again, so if you have one CPU, it's really hard for a type 1 to divide one's resource to all the operating system. Probably what they will do is they will reserve certain amount of CPU cycles to the old operating systems, okay? 10, 10, 10, maybe 100, 100, 100. So they cannot know what is prior here, what is important there. Okay, they are doing some sort of really physical allocations here. So type 1 really allocates, if you have a 16 CPU, the type 1 can allocate 2 CPU here. So, and Linux cannot touch the Windows CPUs. This is what type 1 guarantees, okay? And Linux processes cannot touch Windows processes, memory spaces, and etc. This is the type 1 what guarantees. And think about really partitioning of the physical resources into virtual one, okay? Of course, Windows and Linux still sees the one CPU, okay, and it executes their operations just like they are running in the real hardware, but they are not really using the hardware all along. Probably type 1, so this is specific to the hypervisor as well, but they are doing really hard partitioning, let's say, in terms of resources. Does this a little bit answers your question? Okay. So I'm getting really a lot of questions and it makes me happy, so.
That's what I'm trying to, by asking question to you.
Okay. So I'm checking the time. We have still.
I think we have 10 more minutes before
Okay.
break.
Okay, great. So we have only one topic before the break. Good for me as well. So memory and Io virtualization. At last, we are going to touch for the virtualization topic. So hypervisors again provides this to the guest OS. Okay. So ideally, one of the most important things is memory management and the operating system point of view. So you need to manage the memory as fair as possible, as good and as secure as possible. So page tables, as we know, right, makes the physical memory into virtual. So all the memory divided up to pages and stored in the page tables. Most of the hardware putting their effort into hardware virtualization to spin things up. But if think about hypervisors should all translate things to the physical world. So they are using very early hypervisors. They are doing it. Okay, shadow page tables. They are really managing these page tables in software by themselves. They are also keeping page tables in memory. Okay, and then they are mapping page tables into the tables in the OS. Okay, they are running just like a process, and this hypervisor has a page table by itself, and they are mapping all the arranging page tables to all the guest OSs by keeping the shadow page tables in memory. So this is really slow and not used efficient technique when it comes to the memory virtualization. What it used currently is extended page tables, which is hardware accelerated, provided directly from the CPUs. So all the chipsets. So hypervisor takes this advantage via the host VM. All type 1 hypervisors use this immediately. So it is hardware accelerated. So there is a page tables in the memory, and there is an extended page tables section in the memory, and hardware doing all the translation. It is just one layer back. Okay, so there is a page tables and the MMU, and there is also extended page tables. Next to the page tables, they are one step further abstraction. Okay, they are doing one step further abstraction. Physical memory, virtual memory, and think about virtual memory inside of virtual memory. And this is done by extended page tables. Same technology, same technique what you have seen in the course. So they are just doing sections, pointers to each other, and they are just kind of swapping memories, okay, via the page tables. Okay, same kind of execution via interrupts and page faults again. So exactly the same thing. And this is actually really efficient use of dynamic allocation of the memory throughout the guest OSs, because when you install a guest OS, it requires some certain portion of memory. Let's say if you have a 20 gigabytes of RAM in the physical machine, and if you want to run 3 OSs, virtual OSs, each demanding 10 gigs. So you don't have 30 gigs, right? And it is kind of pity not running these VMs on your physical machine, because they are not demanding this 10 gigs all alone. So they are not allocating this 10 gigs lifetime of this their execution, let's say. So what hypervisors doing is they are not allocating 10 gigabytes completely from the beginning to the end. What they are doing is they're kind of managing the memory just like an operating system, and giving the memory to the guest OSs exactly what they need, the portion of the memory what they need. If guest OS wants to allocate some portion of the memory like 5 gigs, 8 gigs, hypervisor uses the 8 gigs of memory from the real device only, okay? Of course, the guest OS is privileged to allocate 10 gigs. If it is so, hypervisors try to allocate it, but then it's kind of a problematic situation begins, so maybe it's getting some sort of Malloc failures, right? Because there is no memory. But if you think about virtual machines, virtual memories, there is always a memory, but there are certain of situations, because if you think about 10 gigs of memory, okay, and virtualization environment, and OS maybe just restricted the 10 gigs, so you're getting some sort of Malloc failures. Okay, maybe in your programs you don't get it, but if you're running big amount of, let's say, big programs demanding a lot of memory, you would get a Malloc error, because your software restricted in 10 gigs, it cannot go beyond, because it is virtual allocated. So we're not talking about physical to virtual things that infinite amount of memory you can access. So actually the virtual memory is not, it doesn't guarantee you give all the memory, right? Virtual memory guarantees you the contiguous memory. So these are the different concepts. You can restrict the memory, but the virtual memory is kind of gives you the continuous memory, which is not scattered around the RAM. So what we are talking about here, so you can run more than you have, okay? Hypervisors enables you to do that. If you have 25 gigs, via hypervisors, you can run 10 OSs, each of them is allocating 10, okay? Might allocate 10, but probably never do, but practically you can run, okay? So another thing is hypervisor isolation in technology. So this is what I meant. So you can isolate certain technologies, okay? Probably you cannot isolate the CPU technology architectures, but what you can isolate is maybe USB 2 to 3. Okay, so guest OS doesn't know the USB 3, but host OS does know. You can translate 2 to 3. Okay, you can translate all the hardware abstractions via the hypervisors. This is also good for hypervisors, because, so in the software industry, you know, changing is really painful, right? So if you implement something, even, for example, you're just giving all the example of the NASA, they implement tons of code in Fortran, they're not there to change it to C. So because they have tested a million times, and they're not going to change it probably in the next 20 years, because they are so good and they don't need to change it. So this is the, let's say, a golden rule, just don't change if it is work, right? So most of the companies doesn't change their kind of software if it is working, but think about 10 years from now, all the physical stuff is really doing really good. So we got really great CPUs, great memories, and good stuff in terms of I/O speeding up, memory speeding up. So also we got gig Ethernet, so gigabytes of stuff. So but all the old software doesn't know what it is, okay? And you want to take advantage of these technologies nowadays. So what virtualization is, enables you to take advantage of this by the isolation of technology, okay? And big companies running old software in the new technology, new systems, by putting hypervisor in between, okay? So even in Siemens, we are using ancient tools for time management. So we are just submitting our time, so how many hours I've been working on in this project, etc. So we are using some very old technology, but probably they are running this technology in a VM, because I don't think it is not suitable for running in Windows 10 or latest Linuxes. This is how it is enabled. So, and
there is a very interesting, maybe unrelated thing going on. We are doing just the opposite with the quantum computers. There are no quantum computers available commercially or publicly. So what we do is we write our programs in quantum computing programming languages, but we emulate a quantum computer on a non-quantum computer.
Yeah, Turing machines probably.
Yeah, so we are kind of kind of virtualizing something that's going to happen in the future.
That's right, but this is all sake of development theory, right? You're developing all the algorithms and stuff, but when it is available,
we are going to do just the opposite of
exactly. So we are going to probably run all the nowadays software in the quantum world. Yeah. Probably this will happen. So in, I don't know, 10 or 20 years from now. So last but not least, device remapping. So it also enables, let's say you have a disk, okay, and as well as memory. So what Hypervisors does is it just remaps sector to sector to the guest OS, okay, and then maybe it just remaps to all these USB devices to the guest OS, okay. They are doing also device remapping securely in an isolated way, so that you are using the USB, okay, and then just plug the USB into a computer, and VMware asks you, can I take the control, okay. So Hypervisor technically says you, should I remap this device to guest OS, okay. This is device remapping, so it is just translating all the stuff to the guest OS. This is a small portion of the detail in Io Virtualization. So I think I'm done for the first hour.
15 minutes of break. Let's be around 11:35.
Okay.
Bir çay alalım.
Olur hocam. Sonra ben geleyim bir setup yapmaya çalışayım. Sonra ben geleyim setup yapmaya çalışayım.
Setup'a gerek yok. Oradan bağlayalım, oradan göstersen. Onu kaydetmeyiz o kadar.
Ha okey. Tamam süper. Olur hocam olur.
Anahtarlarımı alayım.
Ben şu an plakatım var da onun için ayrılsam
Ben yoklamamı aldım. Sen yoklamamı aldın, bana niye soruyorsun ya?
Unuttum ben hani. Belki maillere bak nerede düşüyor. Orada var şu an. Soft'taki çok geliyor. Yani Camp'te kaldı. İngilizce testi oldu. Postmodern şu an soft'taki değilim. Ben sorun değilim derse geldim. Artı direkt onu söylersin. Ben de oldum aslında.
yakışır. Biraz çirkin ama evet. Sanırım projection falan da aynı şeyi satıyormuş. Neyiz? Yani. Evet. Biraz kötü. Ama şarj etmiyor. Çok uzun diyor şarjı. Hayır. Ha sende şey var. Taç var mı?
Tuşlar hepsini göremiyorum ya. Ben bunu şey azıcık zorlanmaya gelsin. Çok yapacağım. O yüzden hep eksik kullanıyorum. O yüzden şey şu an program. Çünkü çok fazla sekmeye çıkınca
Tekrar toplantısına girmişsin.
ben toplantısına gidiyorum.
Evet. Ne işin var senin bizim toplantısında? Hayır, orası öyle.
Software'da da şey olmaz.
Müzikler. Müzikler süper. Evet. Şunlar da
Öyle şarkısı ve şu ben girdiğimde o zaman çıktım yani.
okey.
Ben de bir şey res condition bilmiyorum. Ben res condition biliyorum. Ha. Bak bariyeri çarptım. İngilizce'ye getiriyor çünkü ben. Sen tabii soruları yapmadığın için. Mesela bariyeri bilmiyorsun.
Ben tam ders arasında gireceğim. Bir 10-15 dakika konuşsak yeter zaten. Çok uzun bir şey sürmeyecek. Bilgisayar arasında
Ya onlar kolay. Silinti falan. Sinyaller öyle. Silinti alıyor böyle Wonder'a. Çok şaşırdım. Gitsen mi? Sen de zaman. Şey yaparım ben. Ne yapayım? Ben söyleyeyim hocam buradaydı da kötü oldu desem niye bana söylemediler? Hiçbir şey söylemem. Hiçbir şey söylemiyorum. Ne yapayım? Ne ya? Maratona kayıtsız kalmayın. Gebze Denizli yönetiminde tek kategoriye yazılmış bir Gebze Ulus'ta tarım için kayıtlı sonuç şey galiba kuş falan şeyler maraton var.
Maratona gidelim mi? Ama
Belediyeye yani. Belediye mesleğine. Daha önce Amazon'dan alışveriş yaptın mı?
Paranızı alırsanız gidelim.
Hayır, para iadesi baktın mı?
Hiç iade yapmadım. Kaçıyor.
Kaçıyor.
Şeyi alacağım. Peki giderim. Yani sonra
Neye bastın? Niye hatırlattın?
ne?
Onlar dersi engel değil, ben onu düşünüyorum. Hocam da geldi mesela. Sen biliyor musun? Ulan çok olsun, niye cam açmıyorsun? Duyma açın. Eser öyle. Açabildiğin kadar aç. Üstte niye açamıyorum? Ben ne yapmadım? Adamın şimdi bu adam başka bir ödev mi? Bu ödevden başka sen bir ödev yapmıyor. Cevabını verme abi, sana şunu söyleyeyim. Ödevin mi? Ödevi sorarım ya, o konunun değil. Ben sana şunu sorarım. İlk noktada var, ödev yok zaten. Şimdi ikinci ödevi sağlamıyoruz. Ben de sağlamış kardeşim. Bence var abi. Bence final yani 70 ya. 28 gibi. Geçmene kurtulmuş olsun.
Onun koduna endekslen yani.
35 TL için çok yüksek. Normalde 35 saat. 53 CC. 53 CC. Ya 35'ten aşağı. Yani çan yapmıyormuş yani. 35 TL.
Bırakmayacağım zaten yani. Bu aralar öğrenmediğimiz böyle bir kasvet var ya. O var ya. Termin biliminde de şey oldu. Üstün yüzünden ben de çok
Buna var ya, hep yumuşağı başının altından çıkıyor. Yumuşağı Adem aslında öyle bir kafamda şey yapıyor. Ben de çok
onun için muhabbete dahil olmuyorsun ama adamı götürüyorsun ağları. Bizim burada işte kardeş şurada böyle şey yapalım. Beraber bir toplantı yapalım. Böyle bir mantıklı bir şey yapalım. Birlikte çalışalım.
Ben atıyorum lan. Devam.
Hocam buradan recording'i durdurmak için bir şey yapacak mısınız? Bilgisayarın setup'ı kurayım, başlayacağım.
Ne VGA'n var değil mi?
Var hocam, var.
Şu VGA'yı çıkarıp oraya takacağız.
Tamam. Bak.
Hepsi dahil.
Ya buradan recording falan işleri var ya,
Ben
kaydediyorsun.
kapatırım ben.
Tamam.
Zaten şu anda yani.
Hocanın derste sorduğu sorular.
O zaman 90 abi yok ya.
Bazı şeyler karıştırıyor.
Abi şu